So, good morning to all of you. So, myself Deepak Upadhyay from Impulse Technology, Gurgaon, Delhi. So, study we have already shown how to simulate any material with the help of Nanotechnology and RESCU software. And today, I will cover the device simulation with the help of Nanotechnology, DFT, and NEGF method. So, in the first session, I will show you the features of the device simulation, how to create any device structure, and what property you can simulate from that device. And in the second session, you can do the hands-on practice. So I hope my screen is visible to all of you. So you can see this is my C drive. And in this C drive, I have my device studio folder. So this is my device studio. And my software is located inside this bin folder. Here you can see this is the device studio. So this is the device studio application file. So I would like to start from this scratch. So create a new project, select this OK. Here I would like to enter the project name. So you can see this is my device studio. That is a graphical user interface of the NANODCAL and the RESCU software. And this device studio will help you to build your structure. Either you can build the crystal structure, molecule structure, and device structure. And you can simulate that structure from our simulator. Either you can select this NANODCAL, that is for the Atomistic quantum transport simulator based on the DFT plus NEGF method. Also, we have this RESCU software. That is basically a for large scale material simulation software based on the DFT and DFPT method. So basically this RESCU is dedicated for the material simulation, and this NANODCAL is dedicated for the material as well as device simulation. So device simulation is possible from this NANODCAL software. So here you can see this is the builder. So multiple builder are there. Like this is the molecule 3D builder. This is the molecule 2D builder. And here you can see this is the device builder. So this device builder will help you to build your structure. Here you can see either you can create a left-right device structure, left center right device structure, bottom and top device structure, bottom center top device structure, front and back device structure, front center and back device structure. So up to 6 probe device structure you can easily simulate from the NANODCAL software. So as you know, before creating any device structure, we need some material so that we can create the left electrode, right electrode, either we can create bottom electrode and top electrode. So for creating any electrode, we need some material. So that material either you can import from our local database, either you can import from online database. Also, you can create your own structure from the crystal builder. If you talk about this left-right structure, here you can see. Here we need to define our left electrode material, and then we need to define our right electrode material. So you can see this is the silicon material that I have imported from our local database. And for simulating any material, we can select this simulator. Then we can select this NANODCAL. And in the NANODCAL, you can see multiple options are there. Like this is the virtual crystal approximation. So if you want to include any doping, either p-type doping, n-type doping, then you can go to this VCA calculation. So you can see this is the mixture vacancy. You can also select this mixture atom and you can mix any atom in this structure. Like you can see this is the silicon element. If you want to add any more element, you need to select this add option. You can see default carbon atom is there. You can also change this carbon element with another atom. So you need to double click. Then the periodic table will be open. And from this periodic table, you can select any element. Like this is the phosphorus. And then you can define their composition. So doping is possible from this virtual crystal approximation. And for optimizing any structure, we need to select this relax option. So if you want to do the optimization before going to their analysis, so we need to select this relax option. And you can see this is the relaxation method. So this is the molecular dynamic and this is the conjugate gradient. So we need to go the SCF calculation first. And here, whatever parameter you want to define, you can define and then click on generate file. Hello, yes. So sorry, there is some network issue. So I hope my screen is visual to all of you. So you can see this is the simple procedure for simulating any material with the help of NANODCAL software. So we need to define their SCF input file first. So this is the scf.input file of this structure. And simply you need to run this scf.input file first. Then you can go to the analysis part. You can see these are the analysis parameter that you can study from the NANODCAL software. So any parameter you can select, like this is the band structure. You can click on generate file. Now this scf.input file and band structure.input file has been generated. So we need to run the SCF input file first. Then we can go to the band structure. So this is the procedure with the help of NANODCAL. And if you want to study from this RESCU, so you can see this is the simulator. This is the RESCU. And in the RESCU, you can see multiple options are there. Like also we have this SCF calculation with the help of DFT. Also we have this relax option for optimizing any structure. And we have this density function perturbation theory. So for the phonon density of state, phonon band structure, Raman property, optical property, dielectric property, we can go to this DFPT. And for the band structure, phonon band density of state, local density of state, we can select this SCF calculation. Like you can see, this is the SCF calculation with the help of RESCU software. In the SCF calculation for the crystal, we have two methods. Like first one is real space. Also we have the linear combination of atomic orbital. So any method you can select, click on generate file, then it will generate the scf.input file and atom.xyz file. So in the atom.xyz file, you will find the information of the material. Like you can see this is the silicon atom and their Cartesian coordinate point. And in the scf.input file, you will find the script for this structure with the help of RESCU software. And similarly, you can select RESCU, go to the analysis, and these are the analysis that you can study with the help of DFT, like density of state, Phonon band structure, Malkin population, and potential. Like this is the density of state. Also, you can study projected density of state and local density of state. And click on generate file. Similarly, you need to run the sf.input file first. Then you can go to the density of state. And if we talk about this DFPT, you can see this is the DFPT basic setting in the task. You can see this is the Phonon band structure, Phonon density of state, and in a single click, we can calculate the Phonon band structure and Phonon band density of state. Also, you can see this is the optical property calculation, and this is the Raman property calculation. So for analysis, this parameter, we can go to this DFPT. Like you can see, this is the optical property calculation. You can define the parameter. Like you can see, this is the optic parameter. And once you define the parameter, click on generate file. You can see this is the RESCU DFPT folder. We have the sf.input file, dielectric.input file, phonon.input file, and optical.input file. And whenever the simulation will be completed, then you will get the output file. So this is the procedure for simulating any material with the help of NANODCAL and RESCU software. So today I will cover the device simulation. So for creating any device, first we need to import some material. So as per your device, you can select the material. Like here you can see this is the file option. This is the import option. And I would like to import from our local database. You can see this is the material database. This is the 3D material. This is the conductor. This is the pure metal. Suppose if you want to create a gold-based device structure, then you need to import this gold. And if you want to create a aluminum-based device structure, then you need to import this aluminum. So as per your need, you can select the material. Like here you can see this is the gold. I would like to select this open. Now you can see this is the gold. So this is the gold material that I have imported from our local database. And suppose if you want to show their face center cubic structure, body center cubic structure, then you can select this build. And in the builder, you can see this is the redefined crystal. So for showing the face center cubic structure and body center cubic structure of any crystal, you need to go redefine crystal. So you can see this is the redefined crystal. By expressing the new cell vector UVW as a linear combination of ABC. You can see this is the face center cubic structure and this is the body center cubic structure. You can see this face center has been selected. Preview. So this is the FCC for this gold crystal. Also you can see this is the body center cubic structure. So I would like to select this face center, select this preview, and I would like to click on the build option. So you can see this is the face center cubic structure of this gold material. And if you want to create a supercell of this gold face center cubic structure, so again, you can select this build option, select this redefine crystal, and here I would like to make a supercell in the direction of A, direction B, and direction C. So in the A direction, I would like to select two times in the direction of B, and 4 times in the direction of C. Then it will make a supercell 2 times in the A, 2 times in the B, and 4 times in the C direction. You can see this is the preview. So this is the supercell of our gold phase center cubic structure. So once you click on this preview, then you can click on this build option to build this structure. You can see this is the A direction, B direction, and this is our C direction. Here you can see this is the 3D viewer that will help you to show like XY view, XZ view, YZ view, YX view, and ZX view. Suppose if you want to select this XY view, you can see this is the XY view of our supercell structure. And if you want to delete some atom from this structure, you want to delete this top atom, you need to select the atom first. So you can draw the rectangle, select the atom. Here you can see this atom has been selected. So if you want to select, you can draw the rectangle, select the atom. In the toolbar, you can see this is the delete option. So whenever you click on this delete atom, then this atom will be deleted. Here you can see the atom has been deleted from our supercell structure. And if you want to delete some more atom, like this atom you want to delete, you need to select the atom first. Then you can click on this delete atom. So this is our XY view of the supercell structure. If you select this ZX view, you can see this is the ZX view of our supercell. And if you want to delete some more atom from this structure, like this atom you want to delete, you need to select. So here I would like to deselect this atom and click on this delete atom. Now you can see this is my desired structure that I want to create for the left electrode. So this is my left electrode. And if you want to create a right electrode, here you can see this is the mirrored atom. So we need to select the atom first and then go to the mirror atom. Then it will create a mirror of this structure. So this is my left electrode, and after creating the mirror atom, it will become the right electrode. So left electrode and right electrode. So here you can see this is the mirror atom. And here we can define the normal vector. You can see this is the normal vector XYZ. So in which direction you want to create a mirror? From this normal vector you can select, like you can see this is the XY view, XZ view, and YZ view. You can see this is the XZ view, and here you can define the distance between the electrode. So here you can define the distance between the electrode. Suppose if you want to define 5 angstrom, so you can enter the 5. Then you can enable this copy option. Then you can click on this apply. Then the mirror atom will be created in the XZ position. Now you can click on this apply. You can see in the XZ position, the mirror has been created. So in any direction, you can create a mirror. Suppose if you want to create a mirror in this XY direction, then you can undo this structure, select this structure, then go to this mirror atom. And now here you can select this XY direction. Then it will make a mirror in the XY direction. Again, you need to define some electrode distance and the distance between the electrode. Then you can enable this copy option. Then you can click on this apply. Now you can see in the XY direction, the mirror has been created. And if you want to show all the atom inside the same unit cell, then we need to increase the vacuum energy. So this vacuum energy we need to enable so that all the atom will be in the same unit cell. So for increasing the vacuum energy, we can select this convert to crystal. Here you can see these are the vacuum energy in the direction A, direction B, and direction C. So I would like to increase the vacuum energy 20 angstrom in the A direction, 20 angstrom in the B direction, and here you can see 35 angstrom in the C direction. We need to increase the vacuum energy 36 angstrom. Now you can see. So here you can see the vacuum energy has been created in this structure, and now our all the atom inside the same unit cell. Then you can click on this build option. So if you want to show this atom in the center position, here you can see this is the center option. We can create the center along A, center along B, and the center along C. So you can see this is the center along A, and this is the center along B. So now this is our desired structure that I wanted to create, and this will make as a left electrode, and I will make this one as a right electrode. And suppose in the center region, if you want to create some molecule, so if you want to create a molecular based device structure, if you want to create some molecule, so either you can build your molecule from this molecule 2D builder, 3D builder, either you can import the molecule from our database. So you can see this is my database. I would like to support click on this import local 0D material. Here you can see these are the molecule. So I would like to select this benzene molecule.
Excuse
you can see.
Sir,
Yes, sir.
how can we get the HZW file? Where will we get these files?
Sir, can you repeat? Your voice is breaking.
The importing file HZW file extension HZW. Where will we get these files? These benzene.
Yes, you can get the file from our database. So you can select this import local, and here you can see these are the file in XZW format.
So actually, if I want to do another material which did not having this database, can I get it from Google?
Yes, you can get.
How can I select it?
Here you can see this software support this file format.
Or SIF also support.
Yes, ZIP file you can also import.
Okay.
So either you can import the zip file, .xyz file, .szw file, XSD postcard file, content file. So any file you can import in this device studio.
Okay, correct. Thank you.
And if the file is not supported in this file format, then you can also convert your file. Here you can see this is the convert file option.
Okay.
And you can convert that file into .szw, either .xyz file.
Yes, correct.
And once you converted that structure, then you can easily import.
Yes. Okay. Okay. Thank you.
So you can see this is our benzene molecule that I have imported.
Where is that benzene?
You can see benzene I have created earlier. If you want to create this benzene, you can select this molecule 2D builder. For creating a benzene molecule, you need to select this ring segment first. Here you can see this ring segment has been selected. And for the benzene molecule, we need the single bond that will be connected from this carbon. So I can draw the single. So every side of the carbon, I can create a single bond. And for the benzene molecule, we need to replace this all the CH3 with the hydrogen element. So we can select this carbon, choose element option, select this hydrogen, and we can replace this CH3 with the hydrogen element. So every CH3 we can replace by the hydrogen. You can see this is our benzene structure. And then we can select this apply data. Now you can see this is our benzene molecule. We can apply various force field calculation to minimize this structure. Like you can see, this is the same structure that I have created earlier. So either you can create the molecule from this molecule 3D builder and molecule 2D builder. Either you can import molecule from our local database. So suppose if you want to add this benzene molecule in the center region, so we need to select the benzene molecule first. Here you can see this is our benzene. We need to select all the atom. Now you can see the atom has been selected. We can copy all the atom, Control C. You can go to this structure and here you can Control V. So in this structure, we need to paste our benzene molecule.
Sir, I'm sorry to interrupt in between. Actually, can you repeat once where did you get that benzene? Like you gave the example for benzene. If some other structure I want to, I just want to go through once. I just missed that.
So any material you can import, either molecule, crystal, any structure you can import. Suppose if you want to create a benzene, then you can go to this molecule 2D builder. Select this ring segment. You can add the here. So anywhere you can add this ring segment. Then you can go to this draw single. You can create a single bond from all sides of this carbon element. Like that. And for the benzene molecule, we need to replace the CH3 with the hydrogen element. We can select this choose element, select this hydrogen. Now you can see hydrogen has been selected and we can replace this CH3 with the hydrogen element. Now you can see this is our C6H6 benzene molecule.
Yeah, got it, sir. Thank you.
And then you can select this apply data. Then your structure will be loaded in this device studio. And for adding the benzene molecule in the center, we need to go our benzene molecule. We need to select all the atom. We can copy all the atom, Control C. We can go to our this structure and Control V. Here you can see this is our gold and this is our benzene molecule. If you want to show this benzene molecule in the center, so we need to select this benzene molecule. You can see this benzene has been selected. In the toolbar, you can select this center option. You can see the benzene is in the center position. You can also change this direction of this benzene in the same way as the electrode are there. So if you want to change the direction, so we need to rotate. So if you want to rotate this benzene, you need to select the benzene molecule first. You can see this benzene has been selected. And in the toolbar, you can see this is the rotation. So this is the rotate atom. You can see this is the rotation along screen vector, along XYZ axis, along ABC vector. So I would like to select this screen vector. Here you can define the angle. Suppose I want to define 90 degree. Then you can choose the direction. So in which direction you want to rotate. Like you can see, this is the counterclockwise y-axis. This is the clockwise y-axis. This is the x-axis. And this is our z-axis. So you can see, this is the counterclockwise y-axis. Again, I would like to define 45 angle. This is the 45 degree angle. And I would like to rotate in the z direction. So you can see, this is our benzene molecule in the same direction as our electrode are there. Suppose if you want to create a new atom between these two atoms, here you can see this is the add a new atom option. So if you want to add, then you need to this atom first, then go to this add a new atom. You can click, then the atom will be selected. Now you can see this new atom has been added. Similarly, you can select this two atom. Again, you can click on this add a new atom. This is the property of a whole structure. In this structure, we have 70 atom. This is the vector value, and this is the total area of this lattice. So if you want to replace this, here you can see this is the default gold atom that has been added. So if you want to change this atom, you need to select, and here you can see this is the replace atom. So from this periodic table, you need to click any element. You can see this is the phosphorus, sulfur. So any element you can select and click on OK. Then the atom will be replaced. You can see this is the phosphorus. Again, you can select this gold element, go to the replace atom, select this phosphorus. So to make the connection, so if you want to create the bonding from all the atom, this three atom and this three atom, you need to click on this recalculate linker bond. So it will automatically connected by the covalent bond. So this is the recalculate linker bond. So whenever you click, then the atom will be connected. Now you can see the atom has been connected. So this is my desired structure that I wanted to create. And we can convert this structure into device. So whenever you convert that structure into device, then you will find the left electrode and right electrode and center region. So in the toolbar, you can see this is the convert to device. So this is the convert to device interface. Here you can see various electrode are there. Left electrode, right electrode, bottom electrode, top electrode, front electrode, and back electrode. So as per your device structure, you need to select the electrode. So in this structure, only two electrode is possible. Left electrode and right electrode. So we can select left electrode and right electrode.
Why we have
And
so many atoms in the electrodes?
Yes, sir.
Why we have so many atoms in the electrodes?
So, sir, if you want to reduce, you can delete. So there is no particular reason for adding the atom. So just I am showing a simple example how you can create. Here you can see this is our electrode length. So this is the electrode length in the angstrom. You can also change the length. Here you can see this is the preview. This is our left electrode, and this is our right electrode, and this is our center region. If you want to change the length, like if you want to define -6 angstrom in the left electrode and 6 angstrom in the right electrode, you can see this is our left electrode and this is the right electrode. So the length of this electrode has been increased. So whenever you created the left electrode, right electrode, click on this preview, then you can select this field option. Now you can see this is my 2-probe molecular based device structure, where we have the left electrode, right electrode, and center region. You can see my both electrode are same. This is the gold. So if you want to change any electrode, like if you want to show this gold and if you want to show this aluminum, then you need to select, go to the replace atom. And here you can see this is the aluminum. Now you can see this is our gold based left electrode, aluminum based right electrode, and this is our center region. So this is the procedure for creating any device structure. First, you can create the structure. You can import their left electrode material, right electrode material, and after creating the structure, you can convert that structure into device. By this, convert to device option.
Sir,
Yes, sir.
sir, can I build a PN junction like silicon N type, germanium P type, like semiconducting?
Yes, sir. Semiconducting device you can also create either PN junction, PNP junction. So for the
All
units,
the same procedure. Huh?
yes. So you need to import some semiconductor. Then you can create that structure. And also you can define the doping, N-type doping, P-type doping, and also you can create the NPN junction. Also you can create the MOSFET, like if you want to design some drain, source, gate, you can also design.
Okay, thank you.
So you can see this is my 2-probe device structure, where we have the left electrode, right electrode, and this is our center region. And for simulating this device structure, we need to define DFT parameter in the left electrode, right electrode, and we can define the DFT plus NGF parameter in the center region.
Excuse me, sir. I have one simple query. How did we connected benzene with the our gold electrodes?
So if you want to connect this atom, you can click on this recalculate linker bond. So the atom will be connected.
Right, sir.
This-
Thank you.
This is the recalculate linker bond. And for simulating any device structure, you can see this is the simulator. We need to select the NANODCAL. So device simulation is not possible from the RESCU software. You need to select this NANODCAL. And in the NANODCAL, you can see multiple options are there. Like if you want to make a buffer, like buffer in the sense, if you want to increase the number of atom in the left electrode, right electrode, then you can select this add buffer. Like here you can see, this is the add buffer option. So for increasing the number of atom in the left and right electrode, you can create the buffer. You can see. And for simulation, we need to define DFT parameter so that we have this SCF calculation. And here you can see also we have this transistor option. So we need to define the SCF parameter first. You can see this is the SCF calculation for the device. So this is the basic DFT parameter that we need to define, like their electron temperature, their cutoff energy in the unit of RT, Rydberg, and electron volt, and temperature in the unit of Kelvin. Also, we can define the exchange correlation function, LDA, GGA, their key point sampling. Then we need to move on this contour integral. So this is the contour integral. Also, you can see we have the electrode parameter. Like this is the left electrode parameter and this is the right electrode parameter. We can define the electron temperature, electrode voltage, key point for the left electrode. Also, we can define the electron temperature, electrode voltage, key point in the right electrode. So any voltage you can define here for the left electrode and right electrode. I suppose if you want to define 0.5, you can define. So any value you can define. Suppose here if you want to define minus 0.5, you can say. And this is the iteration control. This is the basic setting. Here you can see our gold, carbon, hydrogen, and phosphorus. Also, you can include the doping. You can see. If you want to define the doping, like N doping in the right electrode, N type doping in the right electrode, and P type doping in the center, you can define. So you can create N, P, N junction. Either you can create a PN junction, either PNP, either NPN. So any structure you can create. Like here you can see, if you want to include the doping, like you can see, N type doping in this side that has been selected, their atomic indices. Similarly, you need to create a doping. Here you can see, I have already created the VCA virtual crystal approximation for the gold and copper waste. So for importing the doping, we need to calculate the VCA calculation first for any atom, either gold, silicon, carbon. So any material you can create. And then you can import their doping. And you can see this is the Spintronics application. You can see this is the no spin, collinear spin. You can see this is the spin polarization, rho value. Also, we have this general spin, rho, theta, and phi. So once you define all the parameter, you can select this generate file. Then it will generate the input file for the left electrode, right electrode, and center region. You can see the sf.input file for the device, the sf.input file for the left electrode, and the sf.input file for the right electrode has been generated. So in the electrode input file, you will find the DFT parameter, and in the device file, device sf.input file, you will find the DFT plus NEGF parameter. Like if we talk about their script, you can see this is the script for this left electrode. In the left electrode, you can see we have the 14 atoms. So these are the gold, their pseudopotential file, and their Cartesian coordinate file. And you can see this is the right electrode. Our both electrode are same. You can see 14 atom in this right electrode and 14 atom in the left electrode. In the device, you can see we have the basic setting. We have the description for the electrode. You can see we have the left electrode and we have the right electrode. You can see this is the contour integral. This is the Spintronics application. This is the iteration control. And in the device, you can see we have 42 atoms. So for simulation of this device structure, we need to run the sf.input file for the left electrode, right electrode. Then we can go to the sf.input file for the device. because as you know, the SF.input file of the device will take the output from the left electrode and right electrode. Here you can see it will take the output from the left electrode and right electrode. So first you need to run the SF.input file for the electrode, then you can go to the device. And here you can see this is the NANODCAL and this is the analysis. So these are the analysis that you can study for the device. Like you can see density of state, effective potential, total energy, scattering state, transmission spectrum, photocurrent, IV curve, charge, electron density, potential, conductance, thermoelectric current, and Seebeck coefficient. So these are the device property that you can study. So if we talk about this density of state, here you can see these are the density of state parameter. This is the scattering state. You can see this is the parameter, K space point, energy point. This is the transmission spectrum and their parameter. So we need to define their key point sampling, N1, N2, N3. Also we need to define the number of energy point. Also you can define the energy range. So this is the transmission parameter. Here you can see this is the photocurrent calculation. So you can also calculate the photocurrent. You can see this is the photocurrent parameter. You can see this is the polarization basis, E1 and E2. This is the polarization vector, like linear polarization, left circular polarization, right circular polarization, elliptical polarization, and oblique elliptical polarization. So these are the various polarization vector that user can select. And also you can change their theta and phi value, their minimum value, maximum value, and their interval. You can also define the photon energy range, minimum energy, maximum energy, and delta E. You can also define the K-point sampling for this photocurrent calculation. Here you can see this is the iridate atom. Suppose if you want to fall the light in the center position, so you can see these are the center position atom. So if you want to fall the light in the center, then we need to select the atom. Then their atomic indices will be selected. So you can see in that atom, the light will be fall. And then you can select this OK. So this is the photocurrent parameter. Here you can see this is the IV curve parameter. You can define the K-point sampling. But already we have defined the voltage in the input, SF input. So here only you can define the K-point sampling. This is the electron density, like charge density, total electron density, row density, bond density. So multiple density are available. Also you can see this is the conductance. You can see this is the K-point sampling. Here you can define the number of energy point. You can see this is the thermoelectric current. We can define the K-point sampling. We can define the temperature. Also we can see, we can calculate the Seebeck coefficient. You can see this is the energy range and this is the temperature. So multiple analysis parameter you can select. You can define their parameter, then click on generate file. Then their input file will be generated. You can see these are the electrode SF input file. This is the device SF input file, and these are the analysis input file. So for running the input file, first we need to run the SF input file for the left electrode, right electrode. Then we can run the SF.input file for the device. Then we need to run all these analysis input file. So this device simulation will take time to simulate. So in the build option, you can see if you want to create a graphene nano ribbon. So here you can see this is the nano ribbon. So this is the graphene nano ribbon builder. We can define the crawl vector and an m value. So either you can create a zigzag structure, either armchair structure. So here you can see this is the 2x2 graphene nano ribbon. Select this preview. You can see this is the zigzag 2x2 graphene nano ribbon. If you want to create an armchair, so you can define m is equal to 0. Then it will make an armchair. Suppose if you want to create a boron nitride based nano ribbon, so you can see this is the site A, site B, and we have the carbon element. So for creating a boron nitride based nano ribbon, we need to select the boron here. In the site A, we can select this boron. In the site B, we can select the nitrogen. Then it will create a boron nitride based nano ribbon. So you can see this is the 4x4 boron nitride based nano ribbon. So any nano ribbon you can create from the changing the site A and site B. So either you can create a graphene nano ribbon, boron nitride based nano ribbon, MOS2 nano ribbon. So any nano ribbon you can create. Also you can change their bond length. You can also passivate with the hydrogen atom. So passivation is also possible. Here you can see this is the hydrogen passivation. And after creating this structure, you can click on this build option to build this structure. So you can see this boron nitride nano ribbon is quite thin. So if you want to increase the length of this nano ribbon, so you can go to this build option, select this redefine crystal. So in any direction you can increase the length. Like here you can see this is the direction A, direction B, this is the direction C. So here I would like to increase the length in the C direction. Now you can see the length of this nano ribbon has been increased in the C direction. So as per your need, you can increase the length. Then you can select this field option. So you can see this is the single layer boron nitride based nano ribbon. If you want to create a multiple layer structure, then you need to copy. Here you can see the atom has been selected. Then you can go to this mirror atom. So multiple layer structure you can create from this mirror atom. We need to define the normal vector first. Like you can see this is the XZ direction. So in that direction we can create another layer. Also we can define the distance between the layer. You can see this is the normal vector. This is the distance between the layer. You need to select this copy. Then you can click on this apply. Now you can see this is our first layer. This is our second layer. So multiple layer structure you can create. And also you can create the defect in your sheet. Suppose if you want to create the defect in this structure, either you can create a point defect, line defect, any defect you can create. So if you want to create a point defect, you need to select any atom and click on this delete. Now you can see the point defect has been created in this structure. Also you can create a line defect. And based on the defect, you can also study how much will be the band gap in your sheet. And also you can convert this structure into device by selecting this convert to device option. You can see we can create the left electrode, right electrode, then select this preview. You can see this is the left electrode and this is the right electrode. So this is the double layer boron nitride based nano ribbon. If you want to create a nanotube, you can see this is the nanotube structure. So this is the nanotube builder. Again, we need to define the crawl vector, then select this preview. You can see this is the crawl vector. If you want to increase the number of crawl vector, like you can see this is the 8. So this is the 8x8 graphene nanotube. So this is the nanotube. Similarly, you can increase their length in any direction. So if you want to increase the length, you need to select this field option. Select this redefine crystal. Here you can see I would like to redefine 15 times in the C direction. And this is our graphene nanotube. So this is the nanotube builder. And here you can see if you want to create a graphene sheet. So disorder graphene like sheet if you want to create, you need to select. Here you can see we need to define the site A atom, site B. Then we can define their bond length. Here we can define the supercell, N1 and N2. You can see this is our graphene sheet. So in a single click, you can create a graphene sheet. So if you want to increase the length, you can. So this is the disorder graphene-like structure. And if you want to rotate your tube at any angle, so here you can see, you need to select the atom first. And you can rotate the tube by selecting this rotation. So you can also rotate like 1.5 degree. In any direction you can rotate. So this is the rotation. And also you can create an interface. You can see this is the interface builder. Suppose if you want to create an interface between the semiconductor, then you need to import the semiconductor material first. Like you can see this is the file. This is the import. This is the import local. We can select this 3D material, semiconductor. And these are the semiconductor that you can import. Like you can see this is the aluminum arsenide. Again, you can import some another semiconductor so that you can create a semiconductor heterojunction. Like if you want to import some gallium arsenide, you can see this is the gallium arsenide. And this is the aluminum arsenide. We need to create a supercell first of both aluminum arsenide and gallium arsenide. Then we can create a heterojunction of this semiconductor. So we need to make a supercell. Here you can see this is the build option. This is the redefined crystal. So I would like to make a supercell 2 times in the A direction, 2 times in the B direction, and 4 times in the C direction. Now you can see this is our supercell of this aluminum arsenide. And then you can select this build option. Again, you can select this gallium arsenide. Now you can see this gallium arsenide has been selected. Go to this build option. And in the same way, you can create a supercell. So in the same direction, you can create like 2 times in the A direction, 2 times in the B direction, and 4 times in the C direction. Now you can see This is our gallium arsenide supercell. And then you can select this build option. So to make a semiconductor heterojunction, we need to select this build option. Select this interface builder. So this is the interface builder. Here we can see we have the structure A, structure B. We need to import this material, gallium arsenide and aluminum arsenide. So in the structure A, from this arrow, we can select this aluminum arsenide supercell. You can see this is the aluminum arsenide, very redefined structure. Again, we can select this gallium arsenide, redefined structure. So this is our aluminum arsenide supercell. This is the gallium arsenide supercell. We can also change their constant value like their grid size, n range, m range, their rotation, their strain value. And then we need to click on this match option. Here you can see this is the graph between the number of atoms and mean absolute strain. Once you click on this match, you can click on this preview. And you can see this is our semiconductor heterojunction. Here you can see this is the total number of atoms.
Sir,
Yes, sir.
so we can build thermoelectric materials of heterogeneous junction and find the temperature and voltage after the
Yes,
device
sir.
population, right?
Yes, sir. Here you can import any material, then you can create their heterostructure. Any material you can import.
Okay.
So any heterojunction you can create from this interface builder, so that you need to import that material and then you can select this match option. Then you can create the heterojunction. Here you can see total number of atoms is. So you can see this is the total number of atoms. This is the angle. This is the rotation. This is the mismatching. This is the area. This is the strain U. This is the strain V. And this is the strain theta. Here you can see this is the strain first surface. This is the strain second surface. You can click on this match, then select this preview. So this is the strain second surface. Here you can see this is the strain both surface. If you want to reduce the number of atoms, you can see these are the number of atoms, and this is the mean absolute strain. You can click anywhere, any point you can click. Here you can see the number of atoms has been reduced. Select this preview. So this is the heterojunction that you can create. And then you can click on this build option. Now you can see this is the heterojunction between the gallium arsenide and aluminum arsenide. So the device simulation will take some time to simulate this structure. So I have already simulated some structure. So I can open my existing project. So here you can see this is the open project. So you can see the same structure I have simulated earlier at different Vicing voltage. You can see these are the simulation that I have simulated, like transmission spectrum, density of state, Coulomb potential, and total electron density for this device structure. Also, we have simulated their IV simulation. You can see this is the current voltage curve. So if we talk about this density of state, you can see this is the density of state that I have projected with the atom wise. So in the projection, I have selected this atom. So you can see these are the atom first, second, third, fourth. These are the energy range, and this is the number of state per electron volt. In the input file, you can see I have selected the projection with the atom. Here you can see this is the Coulomb potential. So this is the Coulomb potential 3D view. You can see this is the 3D view and this is the 2D view. Like you can see this is the average along x-axis, y-axis and z-axis. You can see this is the planar display. This is the stereoscopic display in the z-axis, y-axis and x-axis. Also you can see this is the 1D view.
So how can we download these pictures? How
So
can
simply
we?
you need to export this. Yes. If you want to download this picture, here you can see this is the export option.
Okay.
And here you can select the format, like which format you want to export.
Oh yes, yes.
So you can easily export your raw data in any format, either text format, JPG, PNG, BMP, PDF, any format. So this is the Coulomb potential in XY direction, YZ direction, and XZ direction. Also, you can see this is the total electron density. So this is the 3D view of the total electron density. This is the 2D view. So this is the 2D view along x-axis, y-axis, and z-axis. You can see this is the planar display. This is the stereoscopic display along z-axis, y-axis, and x-axis. Here you can see this is the 1D view. So various property you can simulate for any device structure. Here you can see I have created multiple projects. Photocurrent you can also calculate. Here you can see we have the photocurrent simulation. You can see this is the photocurrent for this device structure. So this is the WSA2 device and we have simulated their photocurrent. You can see this is the lead first, lead second, and all the lead. And if we talk about the IV curve, so also I have calculated. You can see this is the Graphene nanoribbon device structure, and I have simulated multiple outputs like density of state, transmission spectrum, total electron density, Seebeck coefficient, thermoelectric current, exchange correlation potential, and current voltage curve. Like you can see, in this input I have defined collinear spin. So you can see the Spintronics application has been included. So this is the density of state. You can see this is the spin up density of state. And this is the spin down density of state. And this is the both spin up and spin down. You can see this is the transmission spectrum. Spin up transmission, spin down, and this is the both spin up and spin down. And you can see this is the total transmission spectrum. Also, you can see this is the Seebeck coefficient. So this is the Seebeck coefficient with respect to temperature. Also, you can show the Seebeck coefficient with respect to chemical potential energy. So you can see this is the chemical potential energy for the spin up and spin down. You can see this is the Seebeck coefficient And this is the Seebeck spin and charge coefficient. So this is the Seebeck spin and this is the Seebeck charge coefficient with respect to chemical potential energy. And this is the temperature. And some of the output file will open in the MATLAB. Like you can see this current voltage curve. Either you can import this. So this is the XML file. If we talk about their .mat file, you can see this is the .xml file and this is the .mat file. So this .mat file you can import into the MATLAB. So either you can import this file into the import online, or if you have any download version of the MATLAB, then you can open. So you can see I have simulated multiple projects. You can see this is the bilayer CuPC molecular structure. So this is the molecular based device structure. We have the graphene and we have the CuPC molecule. So here you can see I have simulated their multiple input file, and these are the output file. A transmission, total electron density, Seebeck coefficient, and effective potential. Like you can see, this is the transmission spectrum. So for the IV curve, you can see I have opened my MATLAB. And here I can import my project file. You can see these are my file, input and output file will be there. These are the input. Voltage. Here you can see this is the current voltage curve.mat file. You can double click, then it will be loaded. And here you can type data, then press the enter. You can see this is the voltage V1 0.1, I1 6.8881 into 10 to the power minus 6. This is the voltage V2 minus 0.1 and this is the current I2 minus 6.8. So this is the current I2 minus 6.8881 into 10 to the power minus 6. So you can take this output and for plotting the graph, you can click on this new script. Here you can see I have already written the script for this structure. I have taken the input and output value. You can see I have applied minus 0.4 voltage, minus 0.2, 0 voltage, 0.2 voltage, 0.4, 0.6, 0.8 and 1.6. So these are the voltage and also these are the current that I get from the simulation. On the x-axis, I have defined the voltage. On the y-axis, I have defined the current. And then you can select this run option. You can see this is the IV curve at different biasing voltage, like from minus 0.4 to 1.6 voltage. You can also take the value. You can see this is the voltage and this is the current. So you can also plot the IV curve. Here you can see this is the Graphene nanoribbon device structure. And here you can see this is the voltage 0. This is the current. This is the voltage V2. This is the current I2. So here I have defined the Spintronics application so that we can get the spin current. So this data I can take, go to the new script. Here you can see I have already written the script. You can see this is the voltage V2. This is the I1 total current. This is the I1 spin up, spin down. This is the I2 total current. This is the I2 spin up, spin down. And then you can go to the run option. Now you can see this is the spin current for the 2x2 graphene nano ribbon. Current. This is the I2 spin up. This is the I2 spin down. Similarly, this is the I1 spin down, spin up, and this is the I1 total current. So I hope you learn how to simulate any device structure from the NANODCAL software. So if you have any query regarding this, so you can unmute your mic and ask me the queries. Yes, sir, tell me.
Suppose some magnetic material if you put into this kind of devices means and we want to apply magnetic field. Can you apply magnetic field into this in this kind of devices?
Yes, we can apply. Like here you can see, if you import some magnetic material, like you can see this is the magnetic material folder. You can select anyone. Like you can see this is the FeO3. So if you want to apply the magnetic moment, so you can go to the spin type. You can select this collinear spin. And here you can define the magnetic moment for the Fe and oxygen. So if you want to know the theory behind this spin polarization, so I can share. Here you can see this is the spin polarization calculation in NANODCAL. So the relation are there, like their theory and their equations. Like you can see this is the Spintronics. You can see magnetic material. If you visit this website, then you will be more familiar about this NANODCAL and Spintronics application. Like how you can define their magnetic, ferromagnetic, and anti-ferromagnetic material and their magnetic moment. But in Device Studio, you can define from here spin polarization. You can also enable this spin orbital interaction. You can see. You can see this is the ferromagnetic, non-magnetic, and this is the spin orbital interaction. So whenever you visit our website, then I hope you will be more familiar. Their theory, their background simulation, and what parameter you can define. Yes, you can define the magnetic moment for the particular direction as well for any device structure. So basically from this NANODCAL, you can simulate up to small scale to large scale system. So up to 1000 atoms you can simulate. So up to 1000 atoms you can simulate from the NANODCAL, and up to 10,000 atoms you can simulate from the NANODCAL Plus. And with the help of RESCU software, you can simulate up to 20,000 atoms. And with the help of RESCU Plus, you can simulate 1000 plus atom, 1000K plus atom.
What are the basic requirements to run this software?
So system requirements, sir.
Yeah, system.
So sir, basically we recommended 16 GB RAM and 16 core processor for running the device simulation. But as much as your system is good, you will get the faster result.
So minimum 16 GB RAM and
16 core processor.
16 core processor.
Yes.
Sir, is it possible to run this software in 32-bit computer or mandatory for 64?
No, sir. 64-bit computer is required for running the simulation.
Sir,
Yes, sir.
Is it possible to find the contact resistance of heterojunction of semiconductor?
Contact resistance. Okay, so sir, magnetic resistance you can simulate, but a contact resistance I need to check.
Okay.
Magnetic resistance is possible. Here you can see I can show some.
Okay.
Here you can select only electrical properties and electronics properties.
Okay.
Like you can see these are the property that you can simulate for the material,
Yes, yes.
and these are the property that you can simulate for the device.
We can also find the stress strain or thermodynamic property dynamic.
Sir, hysteresis loss you can't get from this NANODCAL, but there are thermoelectric property you can calculate.
Okay.
Thank you for joining this session. So we will meet at 2 p.m. for the final session.